Alright, so I'm going to do the equinox. This is going to be a 5-part series. Part 1 will be what is the equinox and the calculation. Part 2 is what tools do I need to get the information to get the equinox to work. Part 3 is drawing the equinox in Simple 3D. Part 4 is adding in the sun in Simple 3D. Part 5 is the equinox on the flat plane or flat earth. So let's begin. Let's do the math. So I take 90 degrees minus the so this, you on the equinox, you take your latitude from 90 degrees. So the equinox is 54 degrees above the horizon at latitude 36. So you can take 90 minus 54 is 36, which is the latitude, or you can go the other way around. 90 minus 50 or 36 equals the altitude of the sun, and that's the way I'll be doing it. And so the tilt that I'm using, which is 23.4. And so that pretty much covers part 1. Okay, this is part 2. So for Manhattan, Kansas, on March 20th, the exact time that it will be half and half is at 4:24. So this, first thing I need to do is find the my local meridian. So I go Manhattan, Kansas. And then I go March 20th. Okay, so it's at 1:33, but the altitude is 51. So we're in daylight saving time, so it's really 12:33. So UTC time, so 12:33 would be 18:33. Okay. So the other information for me to get the distance is I gotta use this from the NASA website. The target is the sun. Observer is the geocentric, which is the center of the Earth. Then I do my dates, which is I'm going from 319 to 322 increments of 1 minute. And then I set my edit customs, parent. So I check 4, 20, and 28. And then I set it to kilometers. So then I need 1833. And then I would get the distance. So I converted it. I got that. So then that's pretty much all I need for that. So then we'll go to part 3. Okay, so this is part 3. I'm going to show you the 3 measurements that I'm after. So one's at 75 degrees north latitude, and then one at 39.18, that's Manhattan, and then at 15 degrees. And then we'll see what altitude they are. So I'm going to go ahead and show all 3 here. So for Manhattan, so Manhattan is 39.18. And we know that on March 20th, that it's 51 degrees. Okay. You take 90 minus 30, 9.18 equals. So that's 51. Okay, so we'll change it to, we'll go 75. And then we'll go negative 96. Alright, go select it. So it's straight above. Let's see what that is on March 20th. So it's at 15 degrees. And so at 75, or 90 minus 75 north latitude equals 15, and that's what you have right here. Okay, now let's go to the 15 degree mark. 15.00 comma negative 96.00. That's fine. I'll select it. Select. Boom. Alright, so March 20th. It's at 75 degrees, the sun's altitude. So you take 90 minus 15 equals 75. And that's the measurements I will show. So, alright, so this is part 3, drawing the equinox in Civil 3D. So first off, I need to find the distance from this NASA website. That's what I use. Kind of gives you some pretty cool little details. Radius, solar radius, flatness, surface gravity, mass, energy, sunspot cycle, mass, kilograms, volume, mean density. Pretty cool. So we're looking for March 20th at 1833. So we can't come down here. 1833. So I want to copy that. Convert it to kilometers to feet. And then copy this and dive into here. So this is the orbit of the Earth, and you got the aphelion, and then you got the perihelion. So, and that line right there is 94 million miles. So the length divided by 5280 equals 94 million miles. This one is 91 divided by 5280, 91. So draw that circle, radius, paste it. Okay, so this is how I figure out where the location is for the equinox. So the line goes below here and it goes above here. So I know it's somewhere in between. This stuff right here would not be here, so that's for me to locate it. So so you can see it crosses about where I got it. So I would grab the solstice, because that's where you get your axis from. So I never change the axis. I rotate my position along the axis. So I would grab that, copy that, come over here. So that's why the axis looks the same. But that's my position. Of course, it's going to be different. So let's go into this view. Guess I can show the tilt. I use 23.4. So 3-point. Mention 23.4. Alright. So I chose, so Manhattan is Kansas, or let's see here. So it's at 3918 North Latitude. So I did 1538, my position in Manhattan. I'm in Kansas City though, but and then I did 75 degrees. So let me grab this, and I'll so I go from the red line, says to the equator, to the center of the Earth, and then to my location. Again, angle. So 3918, perfect. So let's do the other two real quick. $15. And then 75. Alright, so just check to see for Manhattan on the 20th if I get 51 degrees at that time. So is what you do. You take 90 minus 39.18 equals, so 50.82, which is 51 if you round it. So see if I match that latitude or altitude of the sun. We'll just go this way. We'll go to XY. Gives me a different view. So we can see, definitely tell that the how the sun is, that's 0. So I go dimension, the sun of the sun's rays are at 0. So so we'll We'll see if I get 51. So angle here to, we'll pick here. Oh, dimension, angle to here. So 50.83, perfect. So that's the local plane for that area. So if you do 75 degrees, so 90 minus 75 equals, so that should be 15 degrees right there. DIM. $15.01, real good. Okay, so at 15 degrees, so 90 minus 15 equals 75. So that's almost, so the sun's coming in, so more direct, it's almost overhead right there. So between here and here, it's almost, but not really. And of course here, that's a lot of sun from that point to that point. So the narrow these two lines are, the greater the sun is over the top of you. Okay, so dimension, angle, so 15.01. So that just proves that it's correct. And so that line from, so is what I do, like these aren't there, whoops. So I take one to the center and then I'll grab this and it goes to the center of the sun, and then I do that for everyone. But I just measured it, so that's that line, which the length for this line divided by 5280, 92 million miles, 92.6. Alright, so here's what I want to do. Oops. We'll pick a point and see if I get the same measurements. Like we'll just pick right here. Copy. Move. So I need a line, that red line, to here. So rotate. Reference. And it spins along. Not doing it well. So rotate. I grab everything. Reference. Just looks funny. Oh, I know. Duh. Gotta do the Z-axis. Okay, now rotate. I think I grabbed everything. Now you can tell it's rotating along that yellow line. So I go reference. I hit this red line. And I'm going to line it to that line I just drew from the sun. So now it's at 180. Okay, now I can take measurements. So I need to draw a line from here and from here and here. We'll just grab that then to the sun. Okay, now I can take measurements. So that line's the sun. So I'll take like my position in the A from here. There. And back down. So dimension. So it's at 29. It's not going to be 51. So we'll go from 63. And I measured, I'm just guessing, 62. If I rounded that, $62.66, so that'd be 63. So that's a pretty good guess. So 63, and that's for Manhattan. So thing's pretty accurate. So I'll go ahead and start. I'll add the sun in here and it'll do some magic there. See there? Alright, so this is part 4. I'm going to add in the sun into AutoCAD so it'll show 12 hours. It'll show the sun half and half. 12 hours and 12 hours. So geolocation. Map. So I want Manhattan's location is 39.18, comma, negative 96.57. And that's Manhattan. So drop the marker here. And see here. Next. Now I want to get my coordinates. Here in Kansas, we got 2 zones. We got one in the north and one in the south. So I want that 83 north. And it's in feet, so next. Right in the middle. And then we hit this way, boom. Now you can see it just added that. So I'm going to take this map off. So it gives you the altitude and everything. Pretty cool. Alright. So I want it. 23 March 20th. And I wanted that to be tell where the do it real dark or whatever. the Terminator line. Alright, so what was that? So we're looking at about 424. I want to get to where it said 51 degrees, so that was at it's daylight savings, yes, and that was at 1:30. Well, it was 1:33. So, and it says 51 degrees. Perfect. Okay, so this is what I'm going to do is get this line so it lines up with the axis. And that's set at 424. So we'll see. We'll go 3. Ooh. Well, the yellow line, make it a little darker. Right here, I guess. We'll go 5. Six. Too much. 30. I want to get it so it's defined. So yellow line is the axis. So that's at 20. That thing said 424. So 424, 430. I don't like it. If I use no daylight savings time, it works. I mean, it's not bad. I go 4:45. Yeah. So it's pretty good. Let's go top view. Plan. Oh, yeah. So right here. So that's the curve of it. I'm playing around now. So we'll see for that day, like for the sunrise and sunset. So, Sun, Kansas, Manhattan. At March 20th. So 6. Alright, that's better. So 738. So we'll see. I got 738. So 7, the dark. That's daylight saving, though. Which would be pretty much would be set at 1 degree at like so 722 at 2 degrees. 7, 15. Got 3 degrees. So 267. Pretty close to 715. We'll go 730. Altitude 0. 7. We'll go 7. 6 degrees. So 6 degrees. (702), 6 degrees, 265. 265, pretty good. Now, on the Terminator line, I'm not sure. So that was at 5, 4. So 38. 38. Yep. I'm being precise though. You got half and half. It could be 240. 240. It'd be half and half there. So 530, that's pretty good. Even though this thing said seasons at 20, so that's 430. I'm at 530. So pretty cool. It's a long ways around there. Alright, here's part 5. Alright. So this guy thought this. So, and I measured, what was it, 92.6. So, almost 93 million miles. This here just does not work at all. So the graph below shows heights of the flat Earth sun for various latitudes. The heights are not consistent or constant, but instead depend on observer latitude. At latitudes closer to the equator than 45, the sun apparent height is over 3,000 miles. At latitudes closer to the poles, the sun height is less than 3,000. So, and this is basically what I got. So, and the reason why it's wrong is so this 30 degrees should be 60. So if that latitude, where's my calculator? So 90 minus 30 is 60. And I got 60. Okay. So that's what I did to all these. And is what you get is you get just different heights of the sun. So that's the heights. I don't care. I mean, if you're from here to here, so this is 3,000 miles right there. So from here, I'm from here to here. That just don't make no sense. Because if you're from here to here, the sun is that much of a difference? So 15 degrees, I mean, that's not even that far away. Okay. So at 15, that's 75. Okay. That's insane. If I'm standing here, the person standing here is going to see the sign, boom, less than 3,000, and then you just walk, or not walk, but that distance is only divided by 5280. You know, 1,058. No, you're not going to see that. That's a height of, oops, length, that's 3,000, so that's another 3,000 feet. It's just 1,000 miles. No way. No. Because, so 15 degrees. So, so 90 minus 15 equals 75. Now I can go to the Earth calculator, or the Earth deal, and you will not get that. So 15 degrees, let's just do that real quick. So 15 degrees, time of day. Comma, negative, 96, whatever, slash, and I'm down Or no, south. So that's 15 there. Pretty close. Alright, so 15 degrees north. Okay. March. th. It's going to be 75. Okay. So at 15, that's why I have that line at 75. And then that's why that sun is, you get different heights. Okay. I don't see a 3,000 mile difference. Or, yeah, 3,000 miles. Well, yeah, I guess that would be. So, still, misspoke there. So from here to here, that would be divided by 52. Still 1,000 feet. It just doesn't do that. Why would the sun go around and create these different heights like that? It's just not. This is not how it works.